We start now the proof of the existence of the Lebesgue decomposition. We will prove the existence in the actually the most difficult case, and then the other cases are easy consequences. So I will explain the proof only in the case when both mu and nu are positive and finite measures. Okay, the general case, okay, sigma is still finite but it's vector valued or r valued. Mu is not finite, but sigma finite, and you just chop the space in countably many places where mu is finite. Okay, so let's prove it in this case. So it's a trick that goes back to the fact that the Hilbert space L2 is canonically isomorphic to its dual. So we do the following. We consider the Hilbert space L2 of the measure space, where as a measure we take mu plus nu, right? So we take both measures. Okay, so let me just write it L2 of mu plus nu. And on this space we consider the function lambda that to every function of L2 assigns a real number the following way. It integrates f with respect to the nu. And pay attention, there is only nu, not mu plus nu. Okay? So you should not see this as some kind of norm in L2 or some length of L2. This is just a function at the moment. Okay. What's clear is that this is linear, and now we will see that this is an element of the dual of L2. Okay. So we plan to show that lambda is in the dual of L2 of the measure mu plus nu, but dual, and hence we can represent or representable as a scalar product with respect to some element in L2. Mu plus nu. Okay, so this is the plan. Let's start showing that this is an element of the dual. Okay, so of course, as a function of f, this is linear. The integral is linear. Okay, so mu is linear. But regarding the continuity, we have to prove there is a bounded operator regarding its continuity. So lambda f, again, by definition, is the integral of f in the mu. This number is, so if you take, okay, the norm of this number, it's bounded by the integral of f d mu. Remember, sorry, it was not mu, was the integral with respect to nu. Now I'm assuming in this proof that nu is a positive measure as well. Okay, so f in the mu. Okay, of course this integral is less or equal than if I add. So these are all positive numbers. I add another positive number. Okay, and just because no, this is the positive number. Now, okay, I can write this as the integral of the function norm of f in the mu plus nu. Now I apply Cauchy-Schwarz because I can see this as the integral of f times 1 in the mu plus nu. So this is the scalar product between these two functions. So now by Cauchy-Schwarz, this is less than the norm, the L2 norm of f plus the L2 norm of 1. And now this number here is finite because we assume that mu and nu are finite. So this is a number, it's a constant that only depends on the space and the measures. And now we prove that the value of the measures, it's bounded by this constant times the norm of f in the space we are considering, L2. Okay, so which means that f is a bounded operator. Lambda is in L2 mu plus nu star. Okay, now we know that this space is a Hilbert space. So it's a Hilbert space, and the dual is equal to the space when we identified vectors with the scalar product that they induce. In other words, now we know that there exists some function g in L2 of mu plus nu, such that for all f in L2 mu plus nu, the scalar product f times g is equal to this linear operator lambda of f. In other words, this means that this is the scalar product on L2 mu plus nu. So in other words, the integral of fg in respect to the measure mu plus nu is equal to the lambda of f, which was the integral of f in d mu. Right? So now it's going to be very important that we have this representation. Okay, and now we are going to use this many times. So this is for any f L2 mu plus nu. Okay, we're going to use this property. Okay, so first of all, let's see what this tells us about the possible values for g. So first thing I want to check is that, so what happens if I now take the characteristic of a set, right? So a set is, if the set A has finite measure, then in particular the integral, the characteristic is in L2, and so we know that on the one hand, nu of A, so this is the integral of the characteristic of A in the nu. This is, of course, is a positive number. Now we are going to write this, so this is an f in the mu, f in, okay, here I got it wrong, so this is not mu, it's nu. This was the definition of the lambda operator. Okay, this is nu. Okay, sorry about this. So now we use this equality, so with f, and now we transform it. So this was equal to the integral of the function times g in the mu plus nu. Okay, and now what is this? This tells us that which is the integral over a of g in the mu plus nu. Okay, this tells us that this function g, whenever we integrate on a set, we obtain a positive number, which therefore implies that the function is greater or equal to 0, mu plus nu almost everywhere. Second property, let's change page. Second property, now again, let's take as f the characteristic of a set that is also in L2. Then we have that, okay, the measure of A is positive, and I write this as the measure of A plus the new measure of A minus the new measure of A. And now the first one, I see it as the integral over A, or the integral of the characteristic of A in D mu plus nu, and the second one as the integral of the characteristic of A in D nu. Now we apply so we see this as the operator lambda. So we see that this is the integral of characteristic of A in D mu plus nu minus the characteristic of G characteristic of A in D mu plus nu. So which tells us that the integral over A of 1 minus G in D mu plus nu is always a positive number. And therefore, the function 1 minus G is greater or equal mu plus nu almost everywhere. Okay? So in other words, G almost everywhere is smaller than 1. Now, therefore, up to changing G or mu plus nu null set, we have that G of x is in the interval 0, 1 for all x in E. All right, so now we are ready to define the decomposition. So we define B to be all those points in E for which G of x is equal to 1. And what we were going to do, we shall define nu 0, or not, no, nu 1 as nu restricted to B, and nu 0 is just what's left, nu minus nu 1. Okay, so we need to check that this is the wanted decomposition. Let's remind what this means. This means that by definition, nu 1 of a set A is the integral. It's the measure nu of A intersect B. It's by definition. Okay, for all A in the sigma algebra. Okay, so let's check that this is the wanted decomposition. So let's first check that nu 1 is singular with respect to mu. So first, let's check that nu 1 is singular with respect to mu. So, and we are going to use the set B. So on the one hand, nu 1 of B complement is, as the set, so nu 1 is nu of B, of the set intersect with B. Now this is the empty set, nu of the empty set is 0. On the other hand, so we are going to wonder if mu of B is equal to 0, right? So if I prove this, then nu 1 is concentrated outside B, and mu is then sorry, mu1 is concentrated inside B, and mu is concentrated outside B. So they're singular. Okay, so why this is true? Okay, let's do this calculation this following way. Mu of B can be written as the integral of the characteristic of B in the nu. Now I apply so I see this as the lambda of the characteristic of B, which we can represent it as the scalar product with G in the mu plus nu. Now, what we do now, we use the fact that on B, so outside B this is 0, but on B, G is by definition equal to 1. And therefore this is equal to the integral of 1 characteristic of B, the mu plus nu. In other words, this is equal, so here G is equal to 1 on B. So this is equal to the measure mu plus nu of B, which is mu of B plus nu of B, right? So now we delete mu of B, and we have that 0 is equal to mu of B. Okay, so mu of B is equal to 0. Okay, so we check that mu1 is nu1 is singular with respect to mu. Now let's check that nu0, which is what's left, is absolutely continuous with respect to mu. And we will do that by showing that, I mean, we are showing it, giving the density, that H defined as G over 1 minus G is a density for mu0 with respect to mu. So in other words, I'm saying that mu0 is equal to H times mu. Okay, this is what we want to prove. Okay. Before proving this, let's give a preliminary calculation. So preliminary calculation. So let's fix a set in a sigma algebra, and let's also fix a natural number. So 1 minus G now to the power n plus 1, this is equal to 1 minus G times 1 plus G plus dot 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 plus G to the n. Okay, so this is an equality, it's always true. Okay, so now let's integrate in the nu, integration over A. Okay, so we have this quantity. Okay, now let's split this sum. So this is equal the integral of A of 1 plus G to the n in the nu minus integral of A of G 1 plus G to the n then nu. Okay, now we see okay, we see the first one as a function integrated in the nu. Now we know that this is equal the function, or the function, I should put the characteristic of A as well. So now this is G times 1 plus G to the n integrated in the mu plus nu. Okay, so this is what is the, or maybe let's do it So this is equal to this. So going back to the whole, now you see, now we got the same function, right? Integrated with respect to this measure minus this measure, which now we can remove the two measures, and what we get, this is the integral over a of g1 plus g plus dot 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 plus g to the n with respect to the mu. So we got that this integral is equal to this integral here. Okay. Now let's see what happens to these functions here, one at a time. Okay. First of all, recall that g is in between. Recall that g is in between. G of x is in between 0 and 1 for all x. Now, if and also, so and actually, g is equal to 1 on b by definition of b, and g is in 0, 1, 1 excluded on the complementary. Okay, so now what happens if we take powers? If I'm on b, then this is actually always equal to 1, so it's goes to 1 on b, and g to the n, so if I have a number that is strictly less than 1 and I take powers, then this converges to 0 on the complement, on the other part. This as n go to infinity. So what we understood that the function gn converge pointwise to the characteristic of b, and 1 minus gn converges to the characteristic of b complement. Now what happens to the other functions? We also have that. Okay, let's look at this fact that g times 1 plus g to the n, this can be written as 1 minus g over g. At least this is no, sorry. If we multiply this by this number, we get 1 minus g to the n plus 1, which converges to 1 on b complement. Okay, and therefore what we have that on a new full measure set, recall the mu of b is 0. We have that g1 plus g plus g to the n converges to g over 1 minus g. This one times this one tend to 1, but this is constant, so it means that this function converges to the reciprocal of this. Okay, and this by definition was the function that we called h. So let's go back to the integral equation. We had the integral over a of 1 minus g to the n plus 1 in the mu. This was equal to the integral over a of g1 plus g plus g to the n in the mu. Now what happens is that this function here, we proved that converges to the characteristic of b, and this function converges to the function h. And as you see, the more n increases, as you see here, the more n increases, the more terms I have. And here, we said that it's important what happens in B, in complement of B, because otherwise it's constantly equal to 1. Complement of this is getting smaller and smaller, so bigger and bigger converging to smaller and smaller, but it's between 1, 0, and 1. So both convergence are monotone. So we have monotone convergence, and therefore we can swap limits with integrals. So what does it mean? So this is by definition nu 0 of A. So we this was the complement, and now this is yes. So if nu 1 was nu restricted to B, then nu 0 is nu restricted to B complement. Okay. So now we have, therefore, that this is nu 0, and we represented as a density, the density we want to guess, of times the measure mu. Okay, so this concludes the proof of the existence of the Lebesgue decomposition. The case in which nu is vector valued and mu sigma finite is very easy. It's in the lecture notes.